Okay. Last talk by René Esch. How are you? Esch? Yes. Okay. Thank you.
Thank you for the introduction and welcome to my talk. It's a paper we actually published last year at ICAI, and it's a joint work together with Alessandro Cimatti from the Fondazione Bruno Kessler and my colleagues Jonas, Alexander, and Oliver from the Helmut Schmidt University. And well, thanks to my the previous speakers, everyone already knows what are control parameters. But now let's think of a bit more difficult example, which is more complex. So imagine you want to make cookies, and depending on the kind of cookies you make, you need to adjust different temperatures for your oven, or the cookies have to spend different times in the oven, so your cookies are well done and not burnt in the end. And you can formulate this as a mathematical formula and just insert into the planning problem. But to be honest, if you ask me, I don't know how the mathematical dependencies between the temperature of my oven and my cookies are. So usually I put my cookies in the oven, and then from time to time I check if they are good or not. So what are we doing then? Well, 2 years ago we proposed to use the data, so to use some observations of the system to train a neural network instead, where the neural network approximates the effect of the action, so the effect of the oven, if our cookies are good or not. And well, so to sum it up, we assume we have some real-world system where we have formal descriptions for some of the actions, which we, of course, can directly translate into formal action models. But we also assume that we have some actions where we don't have this formal models, but instead we have some observations. And from these observations, we learn the preconditions. We learn some machine learning models to approximate the effects. And in the end, we need a planner that is capable of handling all those together. So we need a planner that is capable of handling formal action models, including control parameters, in a domain where we have discrete and numerical state variables. And we also need a planner that is at the same time able to handle machine learning models and to integrate them. And 2 years ago, we came up with an eager approach, an eager solution for this, where, as you can see here, we had a physical production system as an example, and you can see the mathematical representation where we have some formal descriptions of the effects. As you can see here, the formal descriptions are actually real mathematical formulas, depending on the different other state variables and some control parameters. And we have a neural network or multiple neural networks for other models. And the first idea was, well, we directly translate this into SMT problem, solve it as a planning satisfiability problem, SMT, and that's it. How did we translate the neural network into SMT clauses? Well, a neural network is actually a bunch of mathematical formulas. And you can describe the output of the neural network, so each output, each different neuron of the neural network, as a mathematical formula over the input and the weights and biases of the network. As soon as you have this mathematical formula, you can put it into a satisfiability problem and try to solve it. Well, that's obviously very, very slow. And you have another problem. You must know the architecture, the weights, and the biases of the network to be able to derive this mathematical formula. And the last problem, the network types that you are capable of to handle are limited to the capabilities of the SMT solver. So for example, linear activation functions are no problem, piecewise linear as well, but it's getting difficult with sigmoid activation functions. So we need to avoid symbolic reasoning about neural networks, and instead we proposed to a hierarchical approach where we separate the reasoning, so the abstract finding of the plan for the parts where we have the action models, and the analysis of the neural network. And this is done with this approach. So we have at the higher level, an SMT solver which solves an abstract planning problem, which gets some lifted information about the neural actions. The neural actions are those actions whose effects are described with the neural network. So the SMT solver gets some information, some lifted information about the neural actions. These are integrated in the satisfiability problem. We search for an abstract plan. As soon as an abstract plan is found, we take the states before and after the action. We take them to the neural networks. We try to find a valid set of control parameters. And then either we get a valid concretization or we add a blocking lemma and search for another plan at the abstract level. Well, let's start with a small example and about with the lifted information we get. So think of the example of the action heat, which increases in this very simple example only the temperature by the value of the control parameter. So no real mathematical formula here. But during the training of the neural network, we check the input and the output states. And what we do is we simply observe which state variable could be changed by this action. So in this case, only the first one. And we update 3 vectors. So the first vector is indicating whether an action is capable of changing the state variable or not. And the second and the third vector is indicating the upper and the lower bound of this change. Of course, all these vectors are updated with every single data sample in the data set. Now, a bit more in detail, what are we doing? Well, we have our planning domain with our lifted information, with our neural networks, and the part of the domain where we have the domain description, the formal domain description, so preconditions and effects for those the actions where we have all this stuff. We generate a satisfiability problem. We solve this with an SMT solver, and actually at this point what's missing here, we unroll the problem like is typical in planning satisfiability. How do we generate the the satisfiability problem, especially with the lifted information? Well, here's the point. That's the information we get from the observer function, so the lifted information, the 3 vectors. What we're doing at this point is for every single vector, for every single state variable, where the vector indicates that the action is capable of changing this, we generate a new variable, which is bounded between the lower and the upper bound. And we simply add this variable as the effect of the action that is replaced by the neural network to the satisfiability problem at the top level, so at the abstract level. Now, when the SMT solver finds a solution, then this solution is a sequence of actions leading from the initial state to the goal conditions. But there are also values for the variables I just showed you. So the variables replacing the effects of the neural actions. And with this information, we are able to derive the explicit states the neural actions are applied to, as well as the resulting state. And with this information, we then go further to the concretization. Here again, a small example. We have our initial state I. We know that in the abstract plan, the first action is action heat, and we know that the temperature is increased by 60 degrees. We can derive S and S prime and give this to the neural network. At this point, let's take a step back and speak about model access. So if you have neural networks or machine learning models in general, you have different types of model access. So either you have a full access white box model, where you know everything, so the model architecture, the weights and biases, and you have also access to the weights. So this is the part where the eager approach was capable of handling this. But you also have the problem that, or the part that you have only a function-based access to the model. So you do not really know the architecture, and you do not really know the weights and biases. But instead, you have dedicated functionalities available, such as backpropagation. And last but not least, you have the complete black box. So you don't know anything about it, you don't have any functionalities. You basically just have an executable where you put something in to get something out. And let's keep this in mind when we talk about how we concretize this. So this is the example for the full axis and the function-based axis, where we have the functionality of backpropagation available. Well, during the training of the neural network, you have the input and the output of the neural network, and you simply update the weights and biases to get the functionality you want, to approximate your function. Well, we propose now to do it the other way around. So we fix all the network, we have our S prime, and we have our S. And what we're doing now is we optimize for the input, for the missing input, which is in this case the control parameter that we need to get from S to S prime. And for full and function-based access models, we use backpropagation for the optimization. For black box models in that paper, we used a beam search because was our first try. But you can also use a bit more or a better optimization technique at this point. So, but what are we doing if we get this, or when we finish the concretization? Well, either we get the result that there is no concretization, so it's unconcretizable. Then we add a blocking lemma, we search for another plan. Or we get a concretization, which means we get a set of control parameters that that leads actually from S to S prime. Well, there's one problem. As we optimize for the last state, it's not possible to reach exactly that state that was assumed or that was given from the abstract plan. Instead, we will get a plan, a state which is within a reasonable distance to the state you want to reach. The reasonable distance is a threshold you have to define. So you need to return this updated state that you reach as well and check if this plan you got is still a good plan, which still leads from the initial state to the goal state. So if you violate some preconditions of the subsequent actions and so on. Well, let's talk about the evaluation. We had 4 different things we wanted to evaluate. So first of all, of course, how does the performance compare to the ego approach, the first one we presented? What influence does the list information have? So the information you get about the neural network beforehand. How does the lazy approach perform with more complex problems? So just scalability. And is the lazy approach capable of solving black box models where you only have a pure input-output interface? To evaluate this, we took 4 domains, so the drone and the xenotravel domain from the numerical track, and we replaced the numerical effects by mathematical formulas, including control parameters. We also took the cache point domain, which was introduced when the control parameters were introduced. However, at that point, we transformed the derivative actions into normal actions because at the moment we are not capable of handling time. And we also used FLIPSI, which is a production simulation. Well, first of all, the comparison of the eager approach and the lazy approach. At this point, we compared only the parts where we have real activation functions because those are the only activation functions the older approach is capable of handling. And as you can see, we set a timeout to 7 days, so 648 seconds, and the eager approach was not able to solve any of the given problems within that time. However, the lazy approach with the full access models was capable of solving the problem within 5 seconds for a really complex domain or a really complex problem, 50 seconds. We also did the ablation study on the lift information, meaning we cut down the lift information we give the solver at the abstract level for the reason that the lift information you get during the training may shrink your search space, so you lose, there's the possibility of losing completeness. So first, we check for the complete information, so all 3 vectors. Partial information, there is only the first vector indicating whether an action is capable of changing the state variable or not. And no information, well, no information. As you can see, there's interestingly nearly no difference between the complete and the partial ones. Actually, the partial one is, in some cases, faster than the complete one. However, if you give the lift info, or if you have no lift information at all, you also run into timeout here, which is thus due to the endless iterations between the abstract level and the concretization, because the abstract planner found some stuff, you then see, well, it doesn't work, just blocking the plan and so on. We also had a look at the scalability. We compared different activation functions and increased the number of hidden layers for the neural networks. We also increased the number of neurons per layer, and we increased the number of neural actions, so the number of actions whose effects are replaced with a neural network. And last but not least, we also look at the model access. So if we have a white box model where we have all of the information available, if we have a function-based access model where we only have dedicated functionalities, such as backpropagation available, and no access where we have a pure input-output interface, the time for the full and the function base is the same at this point because we use the same optimization technique. We use backpropagation. For the beam search in the no access model, it's interesting that for some domains, actually, or for all except the FLIPSI domain, the beam search was faster than the backpropagation approach. This is due to the fact that the bounds of the control parameters in these domains were between 0 and 100, so quite small. In the FLIPC domain, the bounds for the control parameters were between 0 and 1 million. So we went into timeout there, obviously. So the evaluation showed that the lazy approach is significantly faster than the eager approach. The lazy approach can handle neural networks as full access white box models, also as function-based, but, and that's a very important point for us, also no access black box models. The lazy approach can handle different types of activation functions, and the activation function has a neglectable effect regarding the runtime. We can handle large networks, but wider better than deeper. Full partial observer performs similar. So while no observer leads to significantly longer runtimes. And here's the point, the different information may limit the search space in a way that the solution is not within the search space. So key takeaway, we propose hierarchically approach to neural numerical planning with control parameters that trades off completeness for generality and efficiency, where we delayed the analysis of the neural networks until an abstract plan is found. We use the discovery of spurious counterexamples, or we use the counterexamples as a form of static learning, and the refinement is completely numerical and does not depend on complex symbolic reasoning about neural networks. As future directions, we think about the integration of the reasoning about neural networks directly into the SMT solver in a tighter way, following an online integration paradigm, especially because this is not only a relevant problem for the planning community, but also for other parts where you need to integrate trained models into satisfiability problems. We also want to have a look at the integration of some symbolic reasoning instead or in combination with the proposed observer function to get the lifted information. For example, you can use some techniques from the neural network verification domain. And also, we want to extend the approach, of course, to temporal planning. And with this, I'd like to thank you for your attention, and I'm open for your questions.
Thanks. Are there questions? Yes, please.
How did you decide on the values of parameters of the model that you didn't vary?
What did you mean?
In the experimental evaluation, you varied several parameters. Here.
So so we varied the number of hidden layers of the model.
Yeah. So then what?
The number of neurons per layer.
Yeah.
For the model.
Yeah.
And the number of neural actions, meaning the number of actions where we replace the neural network, the effects with neural networks.
Yeah. So then what were the values? How did you decide on the values for the other parameters?
In this case, so you mean in the basic scenario? You mean, yeah, the other scenario, the other parameters were just fine with hyperparameter tuning. So we just tried a lot of different things out and used the best.
Okay.
So you mean especially for the part for the neurons per layer and the number of hidden layers?
Yes.
Yes. Yeah, we just tried out which is best. And
Any other question? Yes.
I'm a little confused with these graphs. Are the lines all just overlapping, and that's why there's only one?
well, we only changed the activation functions in this first example.
Okay.
So here we only used real activation. But yeah, in the first example, they're all overlapping. That's the reason why you don't see anything there.
Can you go to the final slide, please, with the future directions? So here, you mean integration of the reasoning, etc. You mean adding support for theories like real arithmetic with ReLU functions and things like that?
Yes. Something in that direction, so that you directly can kind of handling the neural networks as an additional additional background theory.
Is there already work in the scientific community about this stuff? That you know of?
Not as far as I know. And we are working with this with the guys from FBK on this.
Okay. Okay, so this ends the session. Thank you, everybody, for the attention. Thanks to the speakers.